In 1946, a bankrupt Britain was left in the atomic dark by its own allies. But while the world thought they were merely building a weapon, a group of renegade scientists in Cumberland was secretly wiring a plutonium forge to the national grid. This is the untold investigation into Calder Hall, the world's first commercial nuclear power station that was never meant to be a power station at all. It wasn't built to light your home. It was built to arm a superpower, and the electricity was just the alibi. The story of British nuclear power does not begin with a quest for clean energy, but with a profound and stinging sense of betrayal that would reshape the 20th century geopolitics. To truly understand why the reactors at Calder Hall look so fundamentally different from the American designs you might see in Pennsylvania or Illinois, we have to look at the smoking wreckage of 1946. World War II had ended, but for Britain, victory felt like a slow-motion collapse of everything they held dear. The empire was fracturing, the national treasury was essentially a hollow shell, and the winter of 1946 was the harshest in living memory. Snowdrifts reached 20 feet in the Scottish Highlands, and the railway system, exhausted by years of war, ground to a halt. Coal, the lifeblood of the British economy for 2 centuries, was failing. People were freezing in their homes, and the once mighty British industry was flickering out. But there was a deeper, more clinical chill in the halls of government in Whitehall. During the war, the British had been indispensable partners in the Manhattan Project. It was the British tube alloys probe that had first alerted the Americans to the feasibility of a bomb. Men like James Chadwick, who discovered the neutron, and William Penny, the mathematical genius of blast effects, had provided the essential calculations that made the Trinity test possible. There was a gentleman's agreement, an understanding codified in the Quebec Agreement, that this knowledge would be shared forever. That hope died a sudden death on August 1, 1946, when President Harry Truman signed the McMahon Act. The act effectively terminated all atomic cooperation between the United States and its allies, including its most loyal one. Suddenly, the British were locked out of Los Alamos and Oak Ridge. They were denied access to the data on uranium enrichment and the blueprints for the Hanford reactors. For Prime Minister Clement Attlee, a man not prone to outbursts, this was a moment of cold realization. If Britain wanted to remain a first-tier power and not just a client state of the Americans, it needed the bomb, and it would have to build it in total isolation. This isolation forced a unique, almost desperate path of engineering. The Americans had the luxury of enriched uranium, fuel that is hotter and easier to manage because the concentration of the fissile isotope U-235 has been artificially increased. The British, however, had no enrichment plants. They only had natural uranium, which is mostly the stable U-238. This technical constraint would dictate every bolt, every brick, and every cooling pipe of what would later become Calder Hall. In nuclear physics, if you use natural uranium, you cannot use regular water as a moderator because light water absorbs too many neutrons, killing the chain reaction before it begins. You need a moderator that is incredibly transparent to neutrons. The Americans used heavy water in some cases, but the British turned to the only thing they could manufacture in bulk, graphite of extreme, unprecedented purity. To bridge this gap, they turned to a man named Christopher Hinton. He was an industrial engineer of legendary discipline who had spent his career at Imperial Chemical Industries, ICI. Hinton was not a nuclear physicist. He was a man who understood how to move high-pressure gases and handle corrosive materials. He looked at the problem not through the lens of theoretical science, but through the lens of heavy industry. He realized that if Britain couldn't copy the American water-cooled reactors, they would have to pioneer gas-cooled technology. This was a massive gamble. Carbon dioxide, under high pressure, would be the medium that carried the heat away from the core. It was a decision made of necessity, but it would create a technological lineage that lasted for over half a century. By the late 1940s, the center of this new British atomic world was an unlikely collection of drafting offices in Risley and a converted airfield in Harwell. The mission was terrifyingly clear: produce plutonium at any cost. Hinton faced a monumental task. He had to build a production pile that could sustain a chain reaction using only natural uranium and graphite, and he had to do it while the country was still rationing bread and meat. The first attempts were the Windscale piles. These were massive air-cooled blocks of graphite that were essentially giant chimneys. They were crude, they were dangerous, and from an engineering standpoint, they were an obscenity. Huge fans, the size of houses, blew air through the core to keep it from melting, and that air, now radioactive and piping hot, was simply vented out of 400-foot chimneys into the Cumbrian sky. To Hinton, this was a waste of thermal energy that bordered on the criminal. It was a system that worked for making bombs, but it was useless making progress. As the calendar turned into the early 1950s, the geopolitical pressure reached a boiling point. The Soviet Union had detonated its first atomic device in 1949, far earlier than Western intelligence had predicted. Britain successfully tested its first device, Hurricane, in 1952, but the government wanted more. They wanted the megaton scale power of the hydrogen bomb to maintain their seat at the table with the superpowers. This required even more plutonium and, crucially, tritium. But the British public was weary of austerity. The massive budgets for atomic research were becoming harder to hide in the national ledger. This is where the pragmatic genius of the British civil service intervened. They conceived of Project Pippa, pressurized pile producing power and ashes. The ashes were the plutonium, the grim necessity of the Cold War. The power was the electricity. The idea was to take the basic design of the wind-scale piles, put them inside a massive steel pressure vessel, and use carbon dioxide gas to carry the heat away to a steam generator. If they could sell that electricity to the national grid, they could subsidize the cost of the nuclear deterrent. It was the ultimate dual-purpose. For the American observer familiar with light water reactors, LWR, the Magnox design of Calder Hall is a fascinating mechanical beast. Because it used natural uranium, the core had to be enormous. We are talking about a graphite structure weighing over 1,100 tons, pierced by thousands of fuel channels. The fuel was encased in a special magnesium alloy called Magnox, short for magnesium non-oxidizing. This alloy was a masterpiece of metallurgy. It allowed the uranium to be operated at higher temperatures without the casing reacting with the CO2 gas. However, it had a low melting point, which meant the engineers were always walking a razor's edge. If the temperature climbed too high, the cladding would fail, and radioactive fission products would leak into the gas circuit. The tolerances were microscopic. If a single fuel rod jammed or overheated, the entire reactor would have to be shut down, halting the production of the precious plutonium. One of the most profound technical challenges was the phenomenon known as the Wigner effect. In a graphite-moderated reactor, the neutrons flying around the core actually knock atoms of carbon out of their crystal lattice. This stores potential energy within the graphite, like a coiled spring. If that energy is released all at once, the temperature of the graphite can spike uncontrollably, potentially leading to a fire. The British engineers had to learn how to anneal the graphite, heating it up intentionally to release this energy safely. It was a phenomenon the Americans had encountered at Hanford, but the British were dealing with it on a far more massive scale. This was the hidden danger lurking inside the atomic cathedral. Every few months, the operators at Calder Hall had to carefully manage this release of energy, a process that felt like diffusing a bomb that was already partially detonated. Let's talk about the deception of the peaceful atom. When you look at the newsreels from October 1956, you see a celebration of progress, but the archives tell a story of military optimization. To get high-purity plutonium-239 for a bomb, you cannot leave the fuel in the reactor for very long. If it sits in the core for months, it begins to absorb more neutrons and becomes contaminated with plutonium-240, which makes a weapon unstable. A civilian power plant wants to leave fuel in as long as possible to get every penny of energy out. Calder Hall, however, was designed with on-load refilling. These were massive 400-ton gantry cranes that sat on top of the reactor. They could lock onto a fuel channel, extract a radioactive rod, and replace it with a fresh one while the reactor was running at full power and under pressure. This is an incredibly complex engineering feat that you only undertake if you need a constant, fresh stream of weapons-grade material. It was a plutonium factory that just happened to have a turbine hall attached to it. The construction of Calder Hall was a feat of civil engineering that rivaled the Great Victorian Project. The site at Sellafield was chosen for its isolation and its access to the cold waters of the Irish Sea for the secondary cooling. The most significant hurdle was the pressure vessel itself. In the mid-1950s, nobody had ever welded 2-inch thick steel plates on site to the standards required for a nuclear pressure vessel. The vessel was 37 feet in diameter and 70 feet high. Every single inch of every weld had to be X-rayed, and because the plates were so thick, they had to be heated before welding to prevent cracking. The welders worked in brutal, claustrophobic conditions, knowing that a single flaw could lead to a catastrophic depressurization of the core. The steel itself was a special low-carbon variety, chosen for its ductility under radiation, but even so, the long-term effects of neutron bombardment on steel were largely unknown. It was an experiment on a gargantuan scale. The heat exchangers were another triumph. 4 massive towers stood at the corners of each reactor building. These were the lungs of the plant. Inside, miles of meticulously finned tubing carried the pressurized CO2. As the hot gas passed over the tubes, it turned the water inside into high-pressure steam. This steam was then piped across to the turbine hall. To a casual observer, the turbine hall looked like any coal-fired plant in the Ohio Valley. You had the familiar hum of the Parsons turbines and the smell of ozone and hot oil. But the source of that steam was a silent, invisible fire that no human eye could safely behold. It was a triumph of heat transfer engineering, moving hundreds of megawatts of thermal energy through a gas that most people associate with the bubbles in a soda. The turbines themselves had to be modified to handle the specific steam conditions produced by the gas cycle, which was cooler than a traditional coal fire, but produced in massive volumes. By 1955, the site was a forest of cranes and a sea of mud. Over 5,000 workers were involved, many of them living in temporary camps. There was a sense of national mission that is hard to describe today. This wasn't just a government contract. It was the British response to the American monopoly and the Soviet threat. The engineers were working 80-hour weeks, fueled by tea and a stubborn refusal to let the British nuclear program die. They were building the first of its kind, and there was no manual. They were writing the physics and the safety protocols as they went along. There were no digital computers to model the neutron flux. Calculations were done with slide rules and mechanical adding machines. Every design decision was double and triple checked by hand. The political stakes were equally high. Winston Churchill, who had returned to power in 1951, was obsessed with the idea that nuclear energy would restore Britain's industrial greatness. He saw Calder Hall as a way to prove that the UK was still the workshop of the world. He pushed Hinton and his team relentlessly. The deadline for completion was set not by engineering logic, but by the desire to beat the Americans and the Soviets to the finish line of commercial generation. This pressure led to some of the most innovative and risky decisions in the plant's design, such as the use of carbon dioxide at much higher pressures than previously attempted. It was a race against time, against physics, and against the encroaching irrelevance of the British Empire. When October 17, 1956 finally arrived, it was a master class in global public relations. Queen Elizabeth II, young and embodying the new Elizabethan age, arrived in Cumberland to a fanfare of trumpet. When she turned the lever that fed nuclear electricity into the national grid, it was a moment of supreme national validation. Today, she told the world, we are making history, and for once, the hyperbole was justified. While the Americans had small experimental reactors, and the Soviets had a tiny 5-megawatt plant at Obninsk that was largely a secret, Calder Hall was the first station in the world to produce electricity on a scale that could actually power a region. It was a 60-megawatt statement of intent that would eventually expand to 4 reactors, providing a significant portion of Earth's power. For the American public watching on their black and white televisions, it was a shock. The backward British, still dealing with the end of empire, had beaten Admiral Rickover's shipping port program to the punch in the commercial sector. For a brief window, Britain was the undisputed leader in nuclear technology. They began exporting the Magnox design to Italy and Japan, dreaming of a global export market. It looked like the future was British, and the future was atomic. However, the Magnox design was a dead-end technology. Because it relied on natural uranium and CO2, it was physically massive. The energy density was low compared to the compact American pressurized water reactors that would eventually dominate the world. The Magnox was an engineering compromise, a brilliant, functional, and reliable compromise. But it was a product of 1940s scarcity, not 1960s abundance. It required massive amounts of concrete and steel for relatively modest power output, making it expensive to build even if it was cheap to run. But in 1956, the flaws were invisible. The lights in the nearby town of Workington were being powered by the atom, and the chimneys were not belching black coal smoke. It felt clean, it felt silent, and it felt like the 21st century had arrived years early. However, as an investigator of the archives, we must look at what happened next door just a year. In 1957, the Windscale Pile No. 1 caught fire. It was the worst nuclear accident in British history. The fire was caused by a botched annealing process of the graphite, that Wigner effect we discussed. The fire burned for 3 days, releasing a plume of radioactive isotopes across the UK and Europe. Calder Hall was a different, more advanced design, but the fire cast a long, dark shadow over the entire Sellafield site. The public began to realize that these atomic cathedrals were also potentially catastrophic. The secrecy that had served the military mission now began to work against the civilian mission. The aftermath of the Windscale fire led to a massive increase in safety protocols at Calder Hall. The Shepherd's Crook filters were added to the tops of the stacks, and the monitoring systems were overhauled. The engineers had to live with the knowledge that they were operating a machine that could, if mishandled, contaminate the very country they were trying to save. This changed the culture of the plant. It went from a place of experimental optimism to a place of rigorous, almost religious adherence to procedure. The operators became a breed apart, men who understood the terrifying power of the silent fire in the core. They developed a unique language of nuclear operation, talking about barns of neutron absorption and scramming the reactor with an intimacy that outsiders found baffling. Despite the shadow of Windscale, Calder Hall ran with a reliability that surprised even its most optimistic designers. It became the workhorse of the British nuclear fleet for the next 47 years, through the Suez Crisis, the three-day weeks of the 1970s, and the Thatcher era. It sat on the Cumbrian coast, quietly. It survived the transition from the 20th to the 21st century. It produced the plutonium for the UK's independent deterrent during the darkest days of the Cold War, providing the fissile material for the Polaris and later the Trident warheads. This dual role meant that Calder Hall was always a target. In the event of a nuclear war with the Soviet Union, Sellafield would have been one of the first places hit. The staff lived with this reality, participating in drills that assumed the end of the world was only a 4-minute warning away. The economics of the plant were always a point of contention among those who knew how to read the government's secret ledgers. On paper, Calder Hall provided cheap electricity, but that was only because the military paid a massive premium for the plutonium. If you stripped away the defense subsidy, the cost per kilowatt-hour was actually much higher than coal. But the government didn't care. They were buying two things for the price of one: an arsenal and an industrial reputation. It was a grand sleight of hand that lasted for decades. By the 1980s, when the military mission began to wind down and the focus shifted entirely to power generation, the true cost of the Magnox fleet became a political liability, leading eventually to the privatization of the energy industry and the slow decline of the British nuclear monopoly. In March 2003, Calder Hall was finally switched off. After nearly half a century of service, the turbines stopped spinning for the last time. But you don't just turn off a nuclear power station of this vintage. The decommissioning process is a project that will last longer than the operational life of the plant itself. It is a slow, methodical process of decoring. The radioactive graphite must be handled with extreme care, stored in shielded containers that will last for centuries. The 4 massive cooling towers, once the icons of the British atomic age, were demolished in 2007 in a spectacular controlled explosion, but the reactor buildings themselves remain too radioactive to be fully dismantled for decades. They are atomic ghosts, haunted by the neutrons of the Cold War. For our audience, there is a profound lesson here in the longevity and pragmatism of engineering. We often think of technology as something that becomes obsolete but Calder Hall was a 1940s solution to a 1940s problem that provided a 21st century service. It was a masterpiece of making do. It used CO2 because it couldn't have enriched you. It used graphite because it had to. It generated electricity because it needed to hide the cost of its bombs. Britain didn't build Calder Hall because it wanted to lead a green revolution. It built it because it was a cornered animal, fighting to keep its place in a world dominated by giants. The engineers were not environmentalists. They were patriots and pragmatists who found a way to turn the most destructive force in history into a mundane utopia. The legacy of Calder Hall is visible today in every gas-cooled reactor still operating in the UK. The advanced gas-cooled reactors, AGR, that followed were the direct descendants of the Magnox, using the same CO2 cooling philosophy, but with slightly enriched fuel to increase efficiency. But the world eventually moved on to the American PWR design, which the UK finally adopted at Sizewell. The British dream of an independent gas-cooled nuclear future died with the Magnox, but it was a magnificent dream while it lasted. It showed that a nation could lose its empire and its wealth, but still lead the world through sheer brainpower and industrial grit. As we close the file on Calder Hall, we are left with a story that is quintessentially British, a mixture of high-stakes geopolitics, brilliant back-of-the-envelope physics, and a heavy dose of state secrecy. to the men who built it, and to the generation that grew up in its shadow, it remains a symbol of a time when a few thousand tons of steel and graphite could change the fate of a nation. It proved that a weapon of war could be harnessed, however imperfectly, for the benefit of the common man. The first commercial nuclear plant wasn't a miracle of pure science. It was an industrial necessity born of the Cold War. It was a monument to the era when the atom was both our greatest hope and our greatest fear. As the last of the Magnox generation of engineers fades away, the silent reactor blocks at Sellafield stand as a reminder. We didn't stumble into the atomic age by accident. We were pushed into it by the cold, hard reality of 1940. Calder Hall didn't just light a town. It proved that the most powerful force in the universe is not the atom. It is human ingenuity under pressure. It reminds us that behind every great technological leap, there is usually a story of necessity, a story of competition, and a story of people who refuse to be left in the dark. The investigation into these archives reveals that the history we are told is often the sanitized version. The truth is messier, more dangerous, and far more interesting. Calder Hall was never just a power station. It was a forge for a new world, built in a time of desperation, and its legacy continues to pulse through the grid, a silent testament to the day the British decided they wouldn't just build a bomb, but they would build a future. It stands as a testament to a generation that didn't ask why, but how. And in doing so, they gave us the first flickering lights of the nuclear. Ultimately, Calder Hall is a reminder of the duality of technology. It was a machine that could create both life and death. It provided the energy to run a nation and the material to destroy a planet. In the halls of Sellafield, that tension was lived every day. The scientists who walked those corridors were not villains or heroes. They were men of their time, solving the problems of their time. They took the terrifying energy of the sun and channeled it through pipes and turbines, making it as ordinary as a kettle. And that, perhaps, is the greatest. As we look toward the future of energy, with its talk of fusion and small modular reactors, we would do well to remember the giant of Cumberland. We should remember that the first steps were taken not in a time of plenty, but in a time of scarcity. We should remember that the first commercial reactor was actually a secret military project. And we should remember that the engineers of 1956 did more with slide rules and grit than many can do with supercomputers today. Calder Hall is gone, but the path it blazed remains the blueprint for our nuclear world. It was the first, it was the boldest, and in many ways, it was the most honest machine we ever built. The story ends not with a bang, but with a slow, decades-long cool. But the heat of that first chain reaction still lingers in the 20th century. It was the moment the world realized that the atom wasn't just a threat, it was a tool. And while Britain may have lost the race for nuclear dominance, for one shining moment in 1956, they were the ones who showed us how to turn the fire of the gods into the light of our home. That is the true story of Calder Hall, the plutonium forge that accidentally saved a nation from the dark. For the men who worked the shifts, for the families who lived in the shadow of the cooling towers, and for the nation that watched in awe as the Queen turned the key, Calder Hall was more than just a job or a project. It was the proof that Britain could still do the impossible. It was a monument to the fact that when everything is on the line, when you are bankrupt and alone, the only thing you have left is your mind. And in 1956, the British mind was the most powerful thing in the world. So, as the silent radioactive remains of the reactor buildings continue their long vigil on the Cumbrian coast, we should tip our hats to the investigators, the welders, the physicists, and the politicians who made it happen. They were the pioneers of a new world, a world where the power of the nucleus was no longer a secret of the desert, but a utility of the city. Calder Hall was the first, and though it won't be the last, it will always be the most important. It was the bridge between the age of coal and the age of the atom, a bridge built of graphite, magnesium, and pure, unadulterated British resolve. In the end, the peaceful atom was a myth, but it was a necessary one. It gave us the nuclear industry we have today. It gave us a way to talk about a terrifying technology without losing our minds. And it gave a small town in England the chance to be the center of the universe for a day. That is the power of a good story, and that is the true legacy of Calder Hall. It wasn't just a reactor, it was the narrative that allowed us to step into the future. And for that, we owe the scientists of 1946 a debt that can never be fully repaid. The archives are now closed, but the mystery of Calder Hall remains etched in the steel and concrete of Sellafield. It is a story of what happens when science meets survival. and it is a story that should never be forgotten. For in the heart of that reactor, for 47 years, burned the spirit of an age that was as dangerous as it was hopeful, as secret as it was public, and as British as it was universal. Calder Hall was the beginning of everything, and even in its silence, it speaks to us of the power of human. The transition from the 1946 crisis to the 1956 triumph was not a straight line. It was a journey through the dark, through the unknown, and through the limits of what was possible. It was a journey taken by men who knew the cost of failure and the price of success. They gave us the first commercial nuclear power station, and in doing so, they gave us a glimpse of a world that was no longer dependent on the dead forests of the past, but on the living energy. Calder Hall was the first light in that new, and its glow will never